Hello guys and welcome to this presentation on computer storage. Today we will explore the various components and types of storage used in computer systems, from early technologies like punch cards to modern solutions like flash memory. So let's dive in. So these are the topics of this lecture: components of a computer system, history of computer storage, types of memory, classification of physical storage media, a storage hierarchy, disk subsystem, network attached storage, performance measure of disk, and optimization of disk blocks. So let's see what are the main components of a computer system. Generally, a computer system consists of several components, and we can categorize them into three main types of components: input devices, output devices, and in here, processing and storage. Input devices. These devices allow users to enter data and commands into the computer system, like keyboard, mouse, or touch screen or mic. So these are the input devices. You can say camera, game controller. These are the input units. Then we have processing and storage. This section includes central components responsible for executing instructions and storing data into a computer. So we have like motherboard. We have in motherboard maybe have control bus. Then we have input ports, RAM, output port, data bus. We have central processing unit that is considered as the brain of computer that is used for process the instructions. In most of the modern computers, we have GPU, graphics processing unit, that is used to handle graphics related computation, but also recently is used for heavy computations like machine learning algorithms. We have also random access memory, that temporary memory used for active process. We have RAM, we have cache memory as a high speed memory for quick access by CPU. And then we have output devices. So the output devices display or produce the result of the computer processing. It means data comes from the input devices. They are processed here, and here we can see the output: monitor, display, printer, speaker, projector, headphone, VR headset. These are all considered as the output devices. Let's go back to the history. Computer storage has evolved significantly over time. Early systems used something like punch cards and drum memory, followed by tape storage and floppy disks. So later, zip drives became popular before modern storage solutions emerged. What are the punch cards? Punch cards are used to store and input data by encoding information as a pattern of holes in stiff paper. Then we had drum memory, was an early from a magnetic storage where data was stored on the surface of a rotating metal drum, and that drum was coated with a magnetic material. Then we had tape drives. These tape drives were used to store data sequentially on some magnetic tape, and it was cost effective but slow, so they used for large scale data backup. Then we had core memory. Core memory use tiny magnetic rings, or we can say cores, and they use these cores to store binary data. And at that time, it was widely used in early computers before the advent of semiconductor memory. Then we had floppy disk. These were some kind of portable magnetic storage devices, and they were used to store and transfer data before USB drives and like cloud storage become popular, and the storage was something like 1.44 megabyte. After that, a zip drive was introduced. It was a high capacity removable storage device, and it has been introduced by Lomega. It offered more space than floppy disks, and the capacity of this zip drive was up to 750 megabytes. So computer memory can be categorized into internal memory and external memory. Internal memory, they are also known as primary memory. These are used for fast access and also temporary data storage. So under this category, we have ROM. ROM stands for read only memory. It's a kind of non-volatile memory. It means it permanently stores essential system instructions like BIOS, basic input output system. And then this ROM stores essential system instructions that are non-volatile. It means when you turn off your computer, the data are still there. In here, we have firmware such as BIOS, and this BIOS is used to initialize hardware during boot up, and also it performs power on self test, which is also known as post power on self test, and also loads the bootloader to start the operating system. So this ROM also stores default system settings, microcontroller code for embedded devices, and also permanent software that rarely changes. Next, we have random access memory or RAM. It's a kind of volatile memory. It means temporary store active data and programs, but whenever the computer is turned off, it will be erased. All the data will be erased. So in here we have SRAM and DRAM. These are two types of RAM. SRAM stands for static RAM, and DRAM stands for dynamic RAM. This SRAM is faster and more expensive, and it is used for cache memory. But DRAM is somehow slower than SRAM, but it is more affordable, requiring frequent refreshing. So DRAM can be divided into SDRAM, RDRAM, DDR, SDRAM. So this SDRAM, synchronous DRAM, this operates in sync with the system clock for better performance. Then this RDRAM, Rambus DRAM, this is a higher speed memory used in early gaming consoles and high performance systems. Then we have DDR SDRAM. This stands for double data rate SDRAM. It is widely used type of memory that transmit data on both clock signal edge, and it can improve the speed. Then under this category we have DDR1, DDR2, DDR3, and DDR4. Also later DDR5 has been introduced. Then on the other side we have external memory. So in here the external memory, we also call them as secondary memory, and we use them for long-term data storage and retrieval. So HDD, hard disk drive, these are kind of traditional magnetic storage with moving parts, and these offer high capacity. Then we have SSD, solid state drive. These are faster and more reliable than HDD. Normally in flash memory we use them. Then we have compact disc or CD. These are a kind of optical storage used for music, software, and backup or these things. Then we have USB, Universal Serial Bus. It's a kind of flash-based portable storage that we use for data transfer. And also we have DVD, Digital Versatile Disc. This is also a kind of optical storage. It is similar to CDs, but they have higher capacity. Physical storage media can be classified and evaluated based on several metrics like speed, cost per unit of data, and reliability. So speed with which data can be accessed. So speed refers to the access time or latency of the storage device. And in here, using speed, we measure how quickly data can be read or written from the storage medium. Faster access speed are typically associated with solid state drives and high performance hard drives. So in here we have two key metrics. One is access time, that is in millisecond, and also transfer rate, that is in megabyte per second. Then we have cost per unit of data. This is the cost effectiveness of the storage medium. And in here, we measure the price for a given amount of storage capacity, usually in gigabyte or terabyte. And traditionally, spanning these drives like HDDs tend to be cheaper compared to SSD, but the price gap is narrowing. So the key metric for this one is cost per gigabyte or terabyte. The next one is reliability. Reliability refers to the storage device's ability to function properly without failure over time. A reliable storage medium will have a low failure rate and long operational lifespan. Devices like SSDs are considered more reliable compared to HDD in terms of fewer moving parts. So the key metric that we use here is mean time between failures, MTBF, and also error rate we may use. And also we have data loss on power failure or system crash. Some storage devices are more prone to data loss in the event of an unexpected power loss or system crash. For example, volatile memory like RAM loses data when power is lost, while non-volatile memory like SSD and DDD retain data. So the key metric that we use here, data retention time and cache protection. Then also physical failure of a storage device. Physical failure refers to the breakdown of the storage medium itself due to mechanical failure, wear out, or external factors like overheating or physical shock. So once again, memory in computer can be classified into two main types: volatile storage and non-volatile storage. Volatile storage, they lose data when power is turned off, and the example is RAM. Non-volatile storage retain data without power, and the example is ROM. So let's check them one by one. The first one is cache. Cache memory is the fastest and most expensive from storage. This cache is very close to the CPU because it can provide information to the CPU very fast, but the storage is very less. So it's volatile. It means lost data when power is off, and it is managed directly by the computer's hardware to speed up data access. Then we have main memory or RAM, you can say random access memory. This provides fast access to data, typically 10 to 100 nanoseconds. However, it's volatile and generally limited to a few gigabytes in capacity. The speed is less than cache, but the capacity is more than cache. Then flash memory. Flash memory is a kind of non-volatile. It means retain data without power. It offers fast read speeds but slower write speed. Flash memory is widely used in devices like USB, smartphones, and digital cameras. How flash memory store data? Flash memory store data using a special tiny switch called as floating gate transistor. So these transistors are made from silicon, and which is a kind of semiconductor. Silicon has properties between those of conductor. Some metals like iron or copper, they are conductor, and we have some other items as insulator. So we have conductor like copper. They can pass the current, but insulators like rubber or wood, they can stop the current. They do not pass the current. This means the silicon is something between these two. It can conduct electricity under certain conditions, but not all the time. So, silicon can act both as conductor and insulator. So this property makes silicon ideal for creating electronic components like transistors, and these transistors control the flow of electronic current. So whenever the current is less than threshold, it will be stopped here and represent the value of 0. But when it is more than threshold, it will pass and it will be shown as 1. A flash memory is made up of many tiny switches that we call them as memory cell, and each memory cell can hold a tiny charge, a little electric current, or no charge at all. If the cell has a charge, it means the data is 0. If there is no charge, it means the data is 1. This is how the memory stores binary data, zeros and one. The next one is magnetic disk. Magnetic disk storage like HDD hard drive disks. These are primary medium for long-term data storage. While slower than main memory, but they offer high capacity and cost effectiveness, and they have direct access capability for reading data in any order. Hard drive disk follows direct access, as I said. It means it is possible to read data on disk in any order, unlike magnetic tapes. And then hard drive disks have much larger capacity and cost per byte compared to main memory and flash memory. So let's have a closer look at the HDD, how they work. We call them as HDD or magnetic disk. It's a type of storage device, and they use magnetic fields to store and retrieve data. A hard drive disk consists of several key components, including platters, read and write heads that you can see here, and also spindle, actuator arms, and also controllers. So these platters are circular discs, and they are made of metal or glass, and they are coated with a magnetic material like iron oxide. Data is stored on these platters in the form of magnetic patterns. Then we have read and write heads. These tiny electromagnetic devices sit just above the surface of the platters. The heads are responsible for reading and writing data. Then we have spindle here. This spindle is the central axis that spins the platters at high speed, typically 4,500 up to 7,000 200 rounds per minute. Then we have some actuator arm. This moves the read and write heads across the platter surface. It is controlled by a motor to position the heads over the correct location of the disk. Then we have controllers, and the controller process the commands for reading and writing data and manage the movement of the actuator arm and the rotation of the platters. So here you can see we have the platters, then we have tracks here, and each track is divided into some sectors. So how data is stored here? The platters are coated with a material that can be magnetized. The data is stored by changing the magnetization of the tiny areas on the platter surface. Each small area is called as a bit. So a 1 is represented by one direction of magnetization, you can say to the north, and a 0 is represented by the opposite direction of magnetization, you can say south. So as I said, we have a read and write head. This is positioned extremely close to the platter surface, almost touching it. You can see some image of these heads. This head is responsible for reading and writing magnetically encoded information. The platter itself is divided into circular tracks, with the modern hard disks having between 50,000 or even up to 100,000 tracks per platter. Then each track is further divided into sectors, and these sectors are the smallest unit of data that can be read or written, typically 512 bytes. The number of sectors per track varies between 500 to 1000 sectors on inner tracks, or 1000 to 2000 sectors on outer tracks. Now let's look at how a sector is read or written. The disk R moves the position the read-write head over the correct track, while the platter spins continuously. As the sector passes under the head, data is either read from or returned to the disk. A hard disk typically has multiple platters mounted on a single spindle, usually between 1 and 5 platters. And each platter has its own read and write head, all mounted on a common arm. When accessing data, the system considers all the tracks on different platters that align vertically as a cylinder. So, for example, cylinder I can consist of I track on all platters. The next one is optical storage. It's a kind of non-volatile storage medium where data is read optically from a spanning disk using a laser. CD, DVD, and Blu-ray are some examples. In magnetic storage, mostly it relies on a read-write head. Optical storage reads data by detecting reflections from the disk surface. There are several types of optical disks like CD-ROM, DVD, Blu-ray. The capacity of CD-ROM is up to 700 megabyte. The capacity of a DVD is up to 17 gigabyte, and a Blu-ray can be up to 54 gigabyte. For archival purpose, write once and read many. These optical disks like CD-ROM, DVD, and DVD-R, these allow data to be written once and preserved for a long time. However, there are also rewritable versions that we can rewrite them. It means we can erase information and write again, like CDRW, DDR. It means read and write. These are only reading, but we can read and write, read and write, read and write. So these are some versions that you can both read and write. One key characteristics of optical storage is that read and write speed are slower compared to magnetic disks. So then we have also, as I said, Blu-ray disc BD. In particular, these are widely used for high definition movies because they need more capacity, and they have significantly larger capacity than CD and DVD. So in Blu-ray, they normally use a blue laser, which has a shorter wavelength than red laser used in CD and DVD. So the next one is tape storage. It's kind of non-volatile storage medium, primarily used for backup and archival purpose. One key characteristics of tape storage, it has sequential access. It means data is read and write in a linear fashion. These make it much slower compared to the disk because accessing specific data requires fast forwarding or rewinding the tape. However, despite slower speed, tape storage offers very high capacity with tapes available in size ranging from 40 giga up to 300 gigabyte or more. Another major advantage of tape storage is cost effective because they are much cheaper, and compared to disk storage, these tapes offer significantly lower storage cost, making it preferred solution for organization that they need to store large amount of data or also infrequent accessing data. I can show a hierarchy comparison of this data. So the storage hierarchy is structured to be balanced between speed, capacity, and cost. Cache and main memory, we call them as primary storage. Flash memory and magnetic disk, we call them as secondary storage. And optical disk and magnetic tape, we call them as tertiary storage. So on top, we have cache and main memory. These are the fastest in terms of speed, but capacity is less. And they are volatile and very expensive compared to others. Then we have flash memory. Flash memory offers a good balance between speed and performance, but it is also non-volatile, so it's on medium. Then we have magnetic disks. They provide larger capacity at lower cost, but are slower than flash memory. Then we have optical disks. They are used for distribution and backup, and they offer decent capacity but are slower and less durable. Then we have magnetic tape. They are slowest, but they offer larger capacity, and also they are cost effective for long-term archival storage. The next topic is disk subsystem. Disk subsystem consists of multiple disks that are connected to a computer through a disk controller. So the controller plays a crucial role in managing tasks such as checksum verification and bad sector remapping, and it ensures the integrity and reliability of data storage. Next, let's talk about the disk interface and standards that we have. These standards define how the disk communicate with the rest of the system. And there are several families including ATA, SATA, SCSI, and SAS. So this ATA adapter is a broad range of standard that has been widely used in traditional hard drives. Then we have SATA, serial ATA. It's a kind of evolution of ATA, and it offers faster data transfer speed and more efficient connectivity for modern systems. Then we have a small computer system interface. This is another family of standards that supports a wide variety of devices, and also they offer high performance and versatility. Then we have serial attached SSCI. This is an advancement of CSI and it includes several variants and each variant with different speeds and capabilities to meet the needs of different applications. Then we have a storage area network. This is also known as SAN. It's a kind of specialized high-speed network that provides block level network access to storage. SANs are typically composed of hosts, switch, storage elements, and storage devices, and they are interconnected using a variety of technologies, topologies, and protocols. SANs may also span multiple sites. A SAN presents storage devices to a host such that the storage appears to be locally attached. So we have these storage devices. They compose SAN and computers. Regardless of their location, they can access these SAN to store and retrieve data. Then we have network attached storage NAS. This is a type of network storage that provides a file system interface through network protocols as opposed to the traditional disk system interface. These devices do not require a keyboard or display, and they are typically configured and managed using a browser-based utility program. Each NAS device functions as an independent node on the local area network and is assigned its own unique IP address. So you can share with your family members, your colleagues, or your friends, and whenever you can access to your data stored here. So let's go back to the performance measures of disk. Performance measure of disk focus on two aspects: access time and also latency. So access time is the total time it takes from issuing a read or write request by CPU to start of data transfer. It consists of two components: seeking time and rotational latency. What is the seek time? Seek time is the time it takes to reposition the disk arm over the correct track. So the average seek time is typically half of the worst case seek time, and which is around 4 to 10 milliseconds on typical disks. Then we have rotational latency, the time it takes for the required sector to rotate under the disk head. The average rotational latency is about half of the worst case latency, which is typically 4 to 11 milliseconds depending on disk's rotational speed, ranging from 5,400 to 15,000 rounds per minute. Data transfer rate refers to the speed at which data can be read from or write or written to a disk. Typically, the data transfer rate ranges from 25 to 100 megabytes per second, but this can be lower for disk's inner track due to the way data is physically arranged on the disk. Additionally, multiple disks may share a controller, so the rate at which the controller can handle requests also impacts the overall data transfer performance. So here are some common interface types and respective data transfer rates. SATA, normally 150 megabyte per second, SATA 2, 300 megabyte per second. And then we have Ultra 200, 320 SCI, 320 megabyte per second. SAS is up to 6 gigabyte per second, byte per second, and fiber channel up to 512 megabyte per second. Then we have mean time to failure metric. This is a measure of the average time a disk is expected to run continuously without experiencing a failure. Typically, the MTTF, this is about 3 to 5 years. When a disk is new, the probability of failure is quite low, and the theoretical MTTF can range from 500,000 to 1,200,000 hours. For example, a MTTF of 1,200,000 hours means if you had 1,000 relatively new disks, you could expect about one failure every 1,200 hours on average. Absolutely, MTTF decreases as disk aids. Then we have optimization of disk block access. First, let's define a block. So as I told you already, a block is a contiguous sequence of sectors from a single track on the disk. Data is transferred between disk and main memory in terms of blocks. And the size of block can be 512 bytes to several kilobytes, depending on the disk and system configuration. In order to optimize this performance, we use disk arm scheduling algorithm. These algorithms determine the order in which pending disk access requests are served. And the goal here is to minimize the movement of the disk arm, which directly impact access time and overall performance. One common example of such algorithm is elevator algorithm. This works similarly to an elevator moving up or down between floors. And these try to optimize the order of track access to reduce unnecessary movements. Then we have file organization. File organization refers to how the data blocks are arranged on the disk to optimize access time. The goal here is to store related piece of information on the same or nearby cylinders. So when data is accessed, the disk head does not have to move excessively, and so that improve performance. However, over time, as data is inserted into or deleted from files, fragmentation occurs. This means that free blocks on the disk become scattered, and when a new file is created, its blocks may end up being spread out across the disk. So this scattering increase access time and also reduce efficiency. So the solution to fragmentation is defragmentation. What it does, the fragmentation organizes the data blocks on the disk and it places them closer together in order to improve access time and overall system performance. Next, we have non-volatile write buffer. Non-volatile write buffer works by writing blocks of data to non-volatile RAM buffer immediately instead of writing them directly to the disk. This buffer is typically made of battery-backed RAM, or you can say flash memory. These retain data even if the power is lost. The disk controller writes the data to the disk when there are no other requests or if a request has been pending for some time. This approach reduces the latency of write operations as data can be quickly stored in the buffer while the disk performs other tasks or waits for less urgent writes to be processed. The last one is log disk. A log disk is a disk dedicated to maintaining a sequential log of block updates. This log disk is designated to be fast and does not require special hardware like non-volatile RAM to function efficiently. The use of log disk is particularly important in journaling file system. These systems can write data in safer order to either NVRAM or log disk, and they can ensure that changes are recorded before they are applied to the main file system. This approach helps to prevent risk corruption in the file system as the log provides a reliable record of changes that can be used to store consistency in the event of a system crash or power failure. So, in conclusion, this presentation, I provided a comprehensive overview of the key components involved in computer storage system and their evolution over time. We begin with an understanding of computer components, highlighting the critical role of memory and storage in overall system performance. We then explore the history of computer storage, tracing the development of storage technologies from early systems to modern solutions. Next, we delve into the types of memory, distinguishing between primary and secondary memory, and we discuss their function in storing data and instructions. We also examine the classification of physical storage media, including hard drive, SSD, and optical disk. The concept of storage hierarchy was explored. We then turn our focus in disk subsystem, detailing the structure of disk storage system and importance of factors like performance measure of disk and optimization of these blocks. We also cover the role of network attached storage in providing scalable network based storage solutions. By understanding these concepts, ranging from storage technologies and performance metrics to system optimization, we gain valuable insight into how storage systems are designed, managed, and optimized for efficiency and reliability in modern computing environments. So thank you very much. Please feel free to ask me if you have any questions, either by sending email or leaving a comment below this video. Thank you.